Okay, I think we can get started. I first welcome everyone to this month's APS GPC Climate Seminar. The purpose of the seminar is to introduce those in physics, particularly the American Physical Society, to current problems, physics problems as relates to the Earth's climate and other climates as well. We are particularly eager for student and postdoc participation, in particular for student and postdoc questions. So please do not be shy in asking questions. As usual, the way we'll run this is to keep questions to the chat during the talk, and then if they look like they should be answered right away, if there's some point of clarification, we can do so. And then we will open for a full question and answer series, oral question and answer series at the end. You can either ask your question orally or just post it to the chat. So without further ado, I'm just going to apologize to the speaker in advance. The person who's going to introduce them is not here in the list of panelists, so I didn't prepare a CV. So I will just say personally that I'm very excited to have Pedram Hassanzadeh here, currently at Rice, moving to the University of Chicago in 2024. Pedram is one of my fellow members of the APS topical group on physics of climate. And I think without further ado, I'll just let him take it away.
Okay, great, thank you very much. So today I'm going to tell you about some ideas on integrating physics, data, and scientific machine learning to study geophysical turbulence, extreme events, and climate change. Of course, using data and physics, theory and physics-based models has been the cornerstone of climate science and many other areas in science and engineering for past few centuries. So to tell you why we need new tools like machine learning in climate science, first I'm going to give you some examples about extreme events like heat waves and hurricanes to highlight some of the key questions and challenges that we have in climate science. And as you'll see, in particular, the presence of multi-scale nonlinear interactions in the climate system is one of the major sources of the challenge that we have. And for example, these interactions can lead to major structural uncertainties in our climate models, in the GCMs, which are the main tools that we need to do to provide information about future climate. And this is one of the main reasons that we are looking for new tools and new novel approaches in climate science. So next, I'm going to give you some examples about the promises and challenges of using machine learning in climate science and more broadly in computational physics. And then I'll discuss what I think could be some directions to pursue in the future, which, as you will see, I will emphasize the need for rigorous frameworks to analyze neural networks when they apply to nonlinear systems like the climate system. And as an example, I'll briefly discuss this work that we have been doing on integrating the Fourier analysis of neural networks and the Fourier analysis of nonlinear physics as a way of moving toward providing these rigorous frameworks for analyzing neural networks. So we know that climate change can have major socioeconomic impacts and that extreme weather events can be devastating. These are just some examples of the extreme weather events that I've been working on in the past few years. Two of these examples are about heat waves and one is about Hurricane Harvey. But what was common among them was the critical role that was played by these peculiar weather patterns called blocking events. So you see them in those blue boxes. These are anomalous high pressure systems, basically anticyclonic circulation that can persist for weeks and even a month, and they can drive heat waves, or as I'll discuss soon, they can worsen the effect of hurricanes. Now, we need to understand the effects of climate change across the scales, from the global to the regional and urban scales, like the scale of a state or even a city. But understanding the effects of climate change at the smallest scales, which is actually what we really need for adaptation and resiliency efforts, can be very difficult because, as I'll discuss, it becomes very difficult to reduce the uncertainties that we have in these projections. To give you an example, since Hurricane Harvey, a major question in climate science has been whether in the future it becomes more likely for Texas to get slow-moving storms like Harvey or fast-moving storms like Hurricane Ike in 2008. Now, Harvey and Ike, they were both devastating storms for Houston, but they had different characteristics, particularly in terms of how fast they were moving. And as a result of that, the damage that they caused had different sources. So we like to know which type of hurricanes might become more likely in the future so that we can adapt accordingly. So in some work that we did, and actually started during the Harvey, we found that Harvey was moving north, but then it stalled over Houston because a blocking event showed up over Western US, and blocking events provide clockwise circulation. So it pushed the hurricane down, and so it stalled over Houston, and that's why we got so much rain for 5 days. Now, this might look like a coincidence, but in a paper that we later published, we looked at some of the past events, we looked at future climate simulations, and we found that whether in Texas we get fast-moving or slow-moving hurricanes, it depends a lot on whether there is a high-pressure system, a blocking event over Western US or not. Just to give you another example, you might remember that in 2012, there was major disagreement between the European and the US weather models about the path of Hurricane Sandy. So Sandy was moving north, but suddenly it turned a 90-degree turn and made landfall in New York and New Jersey as the European model predicted. And it turned out, again, this was because a high pressure system, a blocking event showed up here and it pushed the hurricane westward. So it has been known that forecasting the onset of these blocking events can be very difficult for numerical weather models. The European model is one of the best in capturing these. But even in that model, when we look at different weather patterns, the model has the lowest forecasting skill for these blocking events. Now, challenges with forecasting aside, clearly we also like to better understand how the characteristics of these blocking events in these regions might change with climate change. But again, we know that the climate models have a hard time simulating these events. So the current projections are all over the place, which, as you can imagine, can cause major uncertainties for the adaptation and resiliency efforts, leading to these kind of headlines in New York Times and Houston Chronicle. So I picked these events because they're related to where I live and the work that I've been doing, but we can find many examples like this about different types of extreme events all around the world. So clearly we need better tools in climate science so that we can do better forecasting and long-term projections of these kind of extreme events, especially at regional scales. So let's talk about the tools that we currently have in climate science. So since the beginning, we have been using all sorts of observations from the current climate system, from laboratory experiments. We have been looking at paleoclimate data from thousands or even millions years ago. And we have been looking at even other planetary systems. And for example, next month in the same seminar series, Jeff Vallis will talk about what we can learn from paleoclimates and from planetary and even exoplanetary systems. Now in climate science, using theories has been basically, like many other areas in science and engineering, has been the hallmark of the reductionist science approach that many have been following. So in this approach, basically take a complex system and try to reduce it to a simple process or a simple equation. And if we have a good theory, we can fit one parameter and it would tell us how apples would fall on Earth, on Jupiter, or on even an exoplanet that we haven't directly observed. So the outcome of this reductionist approach, a reductionist science approach, is often very generalizable and interpretable. And then in climate science, increasingly we have been using computer models, the climate models, particularly the climate model hierarchy. Now, these tools are now pretty mature to a degree that there were 2 Nobel Prizes in 21 to Hassanzadeh and Menabi for the contributions to the development of these model hierarchies and theories. And if you're interested in learning more about their work, in the same seminar series a couple of months ago, Tiffany Shah gave a great talk about Menabi's work and talked about how over a few decades, Menabi and his colleagues developed a hierarchy of climate models to quantify the effects of the increase in greenhouse gases on Earth's climate. As for Hasselmann's work, there are a number of papers. For example, there's this nice paper by Valerio Lucarini that you can check out to learn more about Hasselmann's work. And as you know, all of the past seminars have been recorded and you can find them on our website. Okay, so we have these great tools, but as great as they are, we still can't use them to fully answer some of these important questions, for example, about extreme events or regional climate projections. And of course, that's because these tools are imperfect. High quality observational records are too short to study extreme events, which are rare. Theories are slow to develop for very complex systems. For example, currently, we do not have a complete theory for those blocking events, although there has been some nice work in recent years finding analogy between blocking dynamics and traffic jam in the highways or shock waves in supersonic flows. And climate models, well, famously, they have a lot of biases and shortcomings. So certainly we need improvements in all these three areas, but in particular, we need to develop better climate models, because when we ask questions about the future, like for forecasting and projections, we have to heavily rely on these models. But we know that simulating the climate system is very challenging. And a major part of the challenge is that we are dealing with a multi-scale, multi-physics nonlinear system. So this cartoon here is just a reminder of a broad range of time scales and length scales that we have in the atmosphere alone. And we can make similar cartoons for the ocean and other components of the Earth system. And again, there have been a number of talks in this seminar series that the speakers talked about the challenges that come from multi-scale nature of clouds, storms, ocean turbulence, or even the biogeochemical cycle. Now, in many applications, we actually want to predict what's happening here in the large and slow scales, but we can't ignore what's happening in the smaller and faster scales because everything is nonlinearly interacting. For example, and in fact, for many processes, we actually know to a good degree the equations that we need to solve, but we usually don't have the computing power to do that. For example, in a typical climate model that these days they have a resolution of around 100 kilometers, everything on this side has to be somehow accounted for. Now, the traditional approach to this has been to use a low resolution numerical solver, which we can call a GCM, to only solve for the largest scales. But to do that, we need to rewrite our governing equations only in terms of the largest scales. And in order to do that, we need these functions P. These are called parameterizations or closures that would tell us something about the smallest scales in terms of the large resolved scales. And I should say that this is also the common approach in many other areas in science and engineering to multi-scale modeling. Now, in climate science, there has been decades of work developing physics-based parameterizations based on theory and sometimes observations. But we know that to significantly improve our climate models, we need much better parameterizations for many critical processes in the atmosphere, ocean, land, cryosphere, biosphere, and at their interfaces. Now, in the past seminars, you might have heard about clouds and ocean turbulence as examples of important processes that need better parameterizations. So here, let me give you another example, and that's about gravity waves in the atmosphere. So these are waves that are generated in the troposphere because of convection or topography, and the waves go to propagate to higher altitudes and they break, and they drive the circulation variability. For example, they drive this important phenomenon in the tropical stratosphere called quasi-biennial oscillation or QBO. These waves also affect the polar vortex variability and the extreme events at the surface. The problem with these waves is that they can be very small. The wavelengths might be just a few kilometers, as you see in this high-resolution simulation that we have done over a tropical region. But this is how a typical climate model with a resolution of 100 kilometers would see these waves. It basically can't capture them. So as a result of that, currently these waves have to be heavily parameterized in the climate models. But the current parameterizations use many assumptions and have a lot of simplifications. And as a result of that, even many of the state-of-the-art climate models cannot produce their own QBO, or the projections, even at the surface, can be different because of the differences in the gravity wave parameterizations. For example, here, I'm showing you the change in the sea level pressure in response to doubling CO2 in the northern hemisphere, obtained using the same GCM, but with two equally reasonable gravity wave parameterizations. And as you see that the hemispheric patterns overall look similar, but there are noticeable differences at the regional scales. And we know, for example, from our work on hurricanes that whether in Texas we get fast-moving or slow-moving storm actually depend a lot on these regional SLP responses. This is also true about blocking events and heat waves and many other kinds of extreme events. So a major question in climate science is, how can we significantly improve these climate models that we have? Now, one idea is to just rely on the increase in the computing power so that we can run these models at higher and higher resolutions, and eventually we can get rid of most of these parameterizations. However, that is a rather incremental progress, and we know that computing power, at least with the conventional hardware, is about to saturate, but also such very high resolution models are slow to run. So we can't run them for a long time, and we can't run them multiple times. And here I want to emphasize that this is something that's important. So to reduce the uncertainty that we have in climate projections, we need GCMs that are accurate, but also GCMs that are fast because in climate science, generally, we are dealing with three sources of uncertainties. So we have what's called epistemic uncertainty, which is model error. So this is usually because of some poor parameterization. But also we have uncertainties that's called scenario uncertainty that comes from the fact that we don't know exactly how much CO2 and other greenhouse gases we are going to really emit to the atmosphere and to the climate system in the next few decades. Also, there is an uncertainty that's called the internal variability uncertainty, and this comes from the fact that the climate system is a chaotic system, so on its own, it will be fluctuating. So this is basically some sort of noise that we are getting. And now we have tools that we can actually quantify the relative contributions of these three sources of uncertainty when we are trying to look at different variables like temperature or precipitation, and whether we are looking at global or regional scales. And as you see in these plots, actually the relative contributions of these uncertainties evolve over time, and it depends on the scales we are looking at and on the variables that we are looking at. But all the three can be important. Now, by developing more accurate GCMs, we can reduce this epistemic uncertainty. But to reduce the internal variability uncertainty, basically we need to have longer simulations to increase the signal-to-noise ratio, and we need to be able to run these models multiple times to look at different scenarios. Now, before discussing some ideas on how we might be able to develop such GCMs, let me tell you a bit more about myself, because as Albion mentioned, major purpose of this seminar series is to encourage students and researchers who are not currently working on climate science to bring their expertise to climate science. So my PhD was actually not in climate science. It was mainly on theory and modeling of fluid flows. So I worked on rotating stratified turbulence, and I did some work on Jupiter's atmosphere and the jets and vortices, including the red spot. And I did some work on astrophysical flows. And I managed to get the word zombie into the title of my PhD thesis because we think there might be these zombie vortices in the dead zones of the protoplanetary disk. Now, for my postdoc, I thought that, well, there are a lot of cyclones and anticyclones and jets on the Earth's atmosphere. So since then, I've been working on two research directions. One is on the dynamics and the climate change response of extreme weather events. And the other one is on developing new methods to better quantify these multi-scale interactions that we have in the climate system, because this is something that we really need to better answer those questions about extreme events. Just to give you some ideas about some of the work in this second direction, so since my postdoc and then later at Rice, we've been spending a lot of time trying to develop linearized models that can approximate nonlinear systems like the climate system. So we have been developing models to do parameterization, to do a spatiotemporal forecasting, or to find forced responses. And in this work, we have been using some ideas from applied math, like Green's functions, basically taking a climate model and perturbing it many times in different wave numbers and frequencies, and looking at the response, basically doing system identification. And we have been using some ideas from statistical physics, like fluctuation dissipation theorem, or ideas from dynamical system theory, like Koopman mode decomposition. And overall, with these kind of approaches, we have made some progress, and some of these tools later become very useful to look at some aspects of climate variability. And I want to say that for the purpose of understanding some of the fundamental aspects of the climate system, still tools developed with these kind of methods are more useful than most machine learning methods, certainly deep learning methods, because these kind of approaches can give you interpretable models. For example, everything we were doing here, these P, A, and L, these were all matrices. So you can look at the eigenvalues and eigenvectors, and they would provide a lot of information about what these models are doing. However, when it comes to improving the state of the art of forecasting or parameterization, we all have learned that we really need more powerful tools. And that's where machine learning and particularly deep learning comes in. And as you will see soon, actually what I'm doing with deep learning is basically the same thing, except that now I'm developing nonlinear models. So starting 2015, 16, like many other people, our group has started looking at some of these machine learning methods that were emerging. And after spending a few years with these methods, and I would say a good number of people in the community are convinced that we have to seriously consider these methods as basically a forced component in this set of tools that we use in climate science. Now, somebody might ask, well, what's new here? We always had the statistical learning and a statistical analysis in climate science. Well, what's new is, first of all, this new powerful set of tools, the deep neural networks that are making major differences in many areas in medical and commercial applications, and in some areas in science and engineering. Additionally, there is a rapid increase in availability of data from the Earth system because of satellites and other sensor networks. And also, as I already mentioned, the progress using the traditional tools has been incremental and even in some cases stalling, for example, when it comes to important problems about extreme events and regional climate projections. But also there is another reason, and this might be the most important one. The power of these deep neural networks is to deal with very complex, high-dimensional systems. And their weakness is lack of interpretability and generalization. So here there is an opportunity to actually combine these tools that we have because they have complementary strengths and weaknesses. Now, that said, scientific machine learning itself is a field that is in infancy. We are still trying to teach these neural nets about the basics of physics and numerical analysis. But that said, I think there is a lot of potential in this integration. Now, there are many ways that we can imagine machine learning can help climate science. For example, we can imagine using some of these techniques to extract more information from the observations that we have. A lot of people are very excited about machine learning directly leading to new knowledge and better theories. And this is something we can discuss at the end. Another very promising direction is to use machine learning to improve the weather and climate models that we have. For example, we can follow that traditional approach, but replace some of those poor parameterizations with parameterizations that have been learned from data, basically data-driven parameterizations. And again, in this direction, there are many ways to do this. For example, if we have physics-based parameterizations that only have parametric uncertainties, we can use some of these machine learning techniques to better estimate these parameters from observations and other high-fidelity simulations. Or if we think that our current parameterizations have major structural errors, this is the case, for example, for gravity waves, we can imagine to train neural networks to learn completely the relationship between the smaller scales and the larger scales. To give you an example, I'm part of a large international project called DataWave that's focused on developing new parameterizations for gravity waves for the next generation of GCMs. So there's a lot that's going on in this project, but for example, one of the things we are doing is that we are building a library of very high resolution regional simulations like the one that's shown here. We have colleagues in Germany doing high resolution global simulations with the German weather model. And to validate these simulations and more, we have observational data, some from satellites, but more importantly, we have observations from Google balloons. If you remember, these are balloons that were used to provide internet, but by looking at their trajectories, we can actually estimate gravity wave fluxes. So one idea in this project is to combine these data sets plus what we know from physics and train neural networks to represent the effects of the smaller scale waves in a typical GCM. Now, to tell you a bit more about how this idea of learning at smaller scales from high resolution simulations work, I'm going to use a rather simple prototype of geophysical atmospheric oceanic turbulence, and that's two-dimensional turbulence. So the equations are shown here. This is basically Navier-Stokes equation. Omega is vorticity, psi is the stream function. This is the nonlinear term, the Jacobian. The Reynolds number is a parameter that would tell us how turbulent the flow is, and we can have forcing and damping. Now, at a modest Reynolds number with enough spatiotemporal resolution, we can actually solve these equations numerically without any more simplification. And we call that direct numerical simulation, or DNS, and we treat these as the truth. Now, doing DNS for climate system and for even many engineering problems is not possible. So what's done in practice is large eddy simulation, or LES, which, as the name suggests, we are only going to solve for the larger scales. Now, to get the equations for LES, we take the original equations and we low-pass filter them. That's what this overbar is. And we know that we can almost write these new equations only in terms of psi bar and omega bar, explicitly in terms of psi bar and omega bar. But at the end of the day, we will end up with a term like this that I'm going to call pi. This is the subgrid scale term that we can't close. We can't explicitly write this term in terms of psi bar and omega bar. Sometimes you see these written in terms of those prime terms. And this is basically where the effect of the smallest scales are. Now, The computational advantage of LES is clear. If we need much lower spatiotemporal resolution to solve these LES equations. However, this disadvantage is that we need a closure model. We need a model so that we can write pi or represent pi explicitly in terms of psi bar and omega bar. So there has been a lot of work trying to develop parameterizations based on physical arguments. One of the first and still widely used models is called the Smogorensky model, where here the key idea is that the smaller scales, we know that they mainly dissipate the larger scales. So maybe we can represent their effects with the eddy viscosity. Now, the problem with these kind of eddy viscosity models is that they are very dissipative. And so the models that use these cannot capture the extreme events. We can see this even in this simple system. Here, I'm showing you the PDF of vorticity. You can think of it as weather in this system. There is a black line here. That's the PDF from the truth from the DNS. And we see that the Smogorensky and its more advanced variants, they can't capture the tails of these PDFs. Like beyond 2 standard deviation, we see that the extreme events are not captured because these models are very diffusive. So one question is, can machine learning do any better? For example, can we train a neural net to learn this mapping between pi and the resolved variables? And you might notice that there are some results with a convolutional neural network with a CNN here, and that's the blue line, which very well matches this true PDF even at the tails. So the answer is yes, but we had to address a major challenge, as I'll discuss, to get this to work. So far, I talked about one approach to using machine learning to improve climate modeling, and that was by developing better parameterizations. Now, in recent years, another approach has also received a lot of attention, and that's fully data-driven modeling. So here, the idea is to just ignore all the equations that we have, and we train a neural network to take the state of the atmosphere or ocean or whatever you are interested in at the current time and predict it at some later time, like a few hours or days later, and then we can put this back and auto-regressively march in time. Now, this kind of approach can be very appealing because once trained, these models are very cheap and very easy to run. So we can do real-time or probabilistic forecasts. These kind of models can improve data assimilation, or we can turn them into fast statistical surrogate models that have many applications. To give you an example, there is a data-driven weather model called ForecastNet that has been developed by NVIDIA with contributions from my group and a number of other groups. And this model has been trained on only 40 years of observation-derived data reanalysis. But as reported in this paper, for day-to-day weather up to several days, and for some extreme events like hurricanes, atmospheric river, heat waves, this model has forecast accuracy that's comparable to the best numerical weather models. But the key is that this model is 100,000 times cheaper and faster than these numerical models. And I should say that now there are even a few other models that have been introduced more recently, and those models can even beat the best numerical weather prediction model. So I would say this has been one of the most exciting, basically, breakthroughs in applying machine learning to climate science so far. Okay, so there are a lot of promises and there has been some progress, but also, as you can imagine, there are a lot of challenges. And a major source of the challenge is that so far what has been used in climate science and many other areas in science and engineering are basically the same algorithms that have been developed for medical and commercial applications. For example, these data-driven weather models, they mainly use transformers, the same algorithm that ChatGPT uses. So they don't know anything about physics. And as you can imagine, those that can cause issues. So I'm going to briefly talk about some of these questions and challenges. And a lot of these apply to pretty much any application of machine learning to climate science. So to start, basically for any application, we have to ask the question of what's that we want to learn. If we are trying to find a cat, it's sort of clear what we want to learn, but that's not so trivial for applications involving the climate system. For example, I mentioned that we want to use neural networks to learn the effect of these smaller scale waves from these simulations and add them to these GCMs. So we need to have a good estimate of what this pi term look like in these high resolution simulations. But we just published a paper when we look at the common methods to do this using different filters or coarse graining approaches or doing Helmholtz decomposition. And we showed that actually we can get pi terms that look very different. So even what the truth is not so clear. Even once we know the pi term, then the question is, what about the pi term we need to learn? Is it enough to just match the patterns of the pi terms, basically using like a L2 norm, as basically most studies do? Well, it turns out that you can show that this is just the first necessary condition to have a successful parameterization. The second necessary condition is to match the interscale energy or entropy transfer. But as this paper showed very nicely in the early 90s, you can actually never find the sufficient conditions for a successful parameterization. As you try to find the sufficient conditions, you get more and more necessary conditions. So basically, the closure problem in turbulence also shows up when you try to find the necessary conditions to learn a successful closure model. Now, these are not machine learning questions. These are, of course, all physics questions, but the answers have major implications for the loss functions that we choose and for the evaluation metrics that we use in our studies. Now, after that, we have to figure out how to do the training with a small amount of data that we usually have in our problems. There's a question of what physics to include, how to learn the rare events, and how to provide uncertainties for the output of these neural networks or other machine learning methods. And then there are three problems that are generally believed to be the most challenging ones for climate applications. One is interpretability. We like to understand to some degree what these methods are learning and why. There's a problem of out of distribution generalization or extrapolation to a different system, which is a major requirement when we are dealing with non-stationary systems like a changing climate. But this is what happens when we ask a data-driven parameterization to work for a more turbulent flow. And I'll tell you more about this example in a few minutes, but we see that everything blows up. And in fact, instabilities, whether it's a blow up or unphysical drift, are very common in applications of machine learning, particularly neural networks to climate and turbulence. And for example, all of these data-driven weather models that have good forecast skill up to 10 days or so, they actually blow up or show unphysical drifts when we run them for weeks or months. So there are promises. There has been some progress, but also there are a number of major challenges. But here I want to argue that we shouldn't be discouraged, and I want to draw an analogy from the history of climate modeling. So there's a 40-year gap between the first successful numerical weather forecast that was done by John von Neumann, and it really started the field of numerical weather and climate modeling and all the achievements that followed from that. And the first time that numerical weather forecasting was tried in 1910 by Richardson. So Richardson basically took this idea that most people at the time thought would not work, the idea of taking the Navier-Stokes equation and initializing it with the observations and then integrating the equations manually over time. So he took this idea, he tried it, and the results were terrible. The solution very quickly blew up, and it was so bad that they never tried it again. And in these 40 years, actually, the atmospheric science ended up with two sides, and there were major feuds between them. So on one side, there were people who wanted to do everything by pattern matching. For example, weather forecasting was based on looking at some catalogs of the past weather patterns. And so basically, they were doing data science. And then on the other side, there were people like Rossby who wanted to use the first principle and who wanted to use the PDEs that we knew, but he just couldn't solve them. And it was sometime in between that Courant and his colleagues who were developing rigorous methods for numerical analysis actually figured out what was wrong with Richardson work, which was the CFL condition. And still it took another 20 years for von Neumann to get his hand on the first digital computer, ENIAC, and do the first successful forecast. So the point I'm trying to make is that for the success of numerical weather and climate modeling, it actually took decades of progress in several different fields. And one thing that was essential there was the development of these rigorous methods for numerical analysis. So I want to argue that in climate science, in applications of machine learning to climate science, we are sort of currently here, except at this time, we are not going to try to abandon one approach in favor of the other, but we are going to combine them because, as I mentioned before, these two approaches, they have complementary strengths and weaknesses. And even further, I want to argue that at this point, we have to use these more mature tools that we have in climate science and combine them with with these amazing advances in the machine learning community and to develop scientific machine learning and even more specifically climate science machine learning. And in doing that, again, I want to emphasize the importance of developing rigorous frameworks so that we can analyze and understand these neural networks when they apply to these kind of systems. So to contribute to these efforts, in the past few years in my group, we have been developing a hierarchy of test cases that goes from a simple system like Lorentz to canonical turbulent flows and to actual weather and climate data. And we have been using this hierarchy the same way that we have been using climate model hierarchy. So we identify questions and challenges here. We go to simpler systems to understand what's happening, maybe develop some new methods, and then we go back to make sure that everything is scalable. So in the time that's left, I'm going to tell you about some work that we have been doing on understanding the instabilities and the questions about extrapolation and interpretability with parameterizations using this hierarchy. So in this work, we have been training convolutional neural networks, or CNNs, to develop parameterizations. And in these CNNs, basically the input is snapshots of the resolved flow from LES, and the output is the pi term, which includes the effects of the smallest scales. Now, many of you might be familiar with the details of CNNs, but I'm going to go through some of the details so that I can introduce a notation that I'm going to use in the next few slides. So regardless of what is the exact application of a CNN, this is the governing equation of a CNN. So this G here, this is called an activation, and this is the output of a channel and a layer. And here it's 128 squared matrix that's the same size as the input and the output. Now the activation from a layer depends on the activation from a previous layer. After these small matrices W, these are called kernels, do convolution on them, which is the operation that's shown here. Now these W's, these are the main thing we learn when we train a CNN. So here there are 5 by 5. We have 4,000 of them per layer. There are 10 layers. So there are million learnable parameters in this CNN. Now, everything is linear. At the end of the day, there is a nonlinear function, an activation function. And we learn these kernels and a small number of biases basically by minimizing a loss function like a mean squared error that's shown here. Now, as much as neural networks are called black boxes, the equations are actually not that complicated, but what makes them look like a black box is that it's hard to know what they have learned and why. For example, this is one of those 40,000 kernels that we have learned in our work on learning parameterizations for 2D turbulence. And it's hard to look at this and see anything meaningful. But in a couple of minutes, I'll come back to this and I'll tell you what these and all these 40,000 kernels are. So once the CNN is trained for unseen samples, it can predict the pi term. So we can couple it to a LES solver and do a simulation. So this is basically supervised learning, or sometimes called offline learning, because we trained the CNN and then we added it, coupled it to the numerical solver. So as you can imagine, you can have an online learning approach where you train a CNN as the simulation is done. And that approach has its own advantages and disadvantages. So in our work, like many other groups, we found that we can train these neural networks on DNS data, and we can develop parameterizations that look pretty accurate between with the common physics frame metric that is the pattern correlation between the pi terms. But when we couple these neural networks to the LES solvers, they all blow up. And there have been a lot of questions about why this happens. Been thought about, well, maybe the pi term isn't accurate. Maybe we need to have a stochasticity. Maybe we need memory, or maybe there is something fundamentally wrong about this offline learning approach. So in this paper that was published last year, we looked a bit more into the physics of what we are trying to learn. So as I mentioned before, we know that in a turbulent flow, the smallest scales mainly dissipate the largest scales. But also we know that the smallest scales can force the largest scales, something called backscattering, or you can think of it as anti-diffusion. Now, when we changed our metric to a metric that was looking at backscattering and diffusion separately, we found that actually we have not learned accurate parameterization. It turned out that learning backscattering from data is much harder than learning diffusion. It's basically, in machine learning, what's called a data imbalance problem. A strong backscattering is rare, so when you don't have enough data, you're not going to learn it well, and backscattering is a forcing on the system, so if it's poorly learned, it can cause instabilities. So what we did in this paper, we just trained a CNN with much more data, and this number got above 0.9. And then we saw the power of deep learning. And those are the results with the CNN that I showed before, the blue line, that as you see, it matches the PDF of the truth pretty well, even at 4.5 standard deviation, because the CNNs that are learned this way, they learn the right amount of diffusion and backscattering. On the other hand, the physics-based models, they cannot capture backscattering, and for diffusion, they're actually too diffusive, so they can't capture the details of the PDF. Now, I should say that backscattering is a real phenomenon, and there's been a lot of work including backscattering in parameterizations of ocean and atmospheric turbulence and engineering turbulent flows, but it always caused problems with instabilities. But with enough data, deep learning can capture this very well. Now, expecting a lot of data is not practical. So now that we know the physics that's important, in the next paper, we included some of these physics in the training process. And we showed that now with much smaller amount of data, we can get the same performance from the CNN. And just to tell you a bit more about what we did here, one of the things we did was to add that second necessary condition as a regularization term in the loss function. And this was a major component of the new framework. So we can get data-driven parameterizations that work well. So the next question is, can these extrapolate? Can we train this on one turbulent flow and ask it to work on a more turbulent flow? So here I'm showing you results with a different system with the Rayleigh-Bernard convection. So what we did is that we trained CNNs for eddy momentum and heat fluxes on this turbulent flow, and then asked it to work for this more turbulent flow. And then we got that unstable simulation that I showed before. So the answer is no, these models cannot extrapolate. And this shouldn't be surprising. None of these data-driven methods, these machine learning methods, should be expected to extrapolate, to work for a very different system. And this is well known in the machine learning community. And they have a solution for it that's called transfer learning. So the idea of transfer learning is that if I have a neural net that is trained well for one system, if I retrain small part of this neural network with a small amount of data from a new system, if this is done right, then this neural net is going to work well for this new system. So we followed that idea here. We took that CNN that was trained for this first flow, and we retrained only one layer, but the right layer, with 1% data from this new system. And then we got this last simulation, which is stable, and it produces the right statistics. For example, if you care about heat transfer, the Nusselt number has been captured well. So by thinking about physics and by using some other machine learning methods, we can make progress and address some of those questions and challenges that I mentioned before. But still, the progress can be slow. We don't have interpretability. I also mentioned that we have to do the transfer learning right. We have to train the right layer. But the question is, what is the right layer? This is currently done just by try and error. So we started thinking that, well, when we study climate data, turbulent flows, many other type of dynamical systems, very often we look at our equations and data in the spectral space, like in the Fourier space, because that's where the physics and the data might simplify and we can find better connections with the theories that we have. So we thought to do the same thing to the neural network. So to remind you, this is the equation of a CNN. So we can write down the Fourier transform of this activation function G. To do that, this blue part, this is all linear, I'm going to call it H. And we can use the convolution theorem to go between these from here to here, where basically we get an element-wise multiplication between the Fourier transform of the kernel and the Fourier transform of the activation. Even though there is a nonlinear function here, I can still analytically write down the Fourier transform of this G, and I get this sum, which comes from how the ReLU operates. The point is that this analysis shows that what determines the Fourier transform of the activation from a layer to a layer, and eventually from the input to the output, is this sum, but more importantly, it's the Fourier transform of the kernel, which basically suggests that instead of looking at these kernels in the physical space as these 5x5 matrices, we should look at their Fourier transform. Now, remember that these are 5x5 matrices doing convolution on 128 squared matrices. So to get their Fourier transform, we can just pad it to 0 to 128 squared and then do 2D FFT. And this is what we get. So this basically tells us that this kernel is some sort of filter that's zero everywhere, except for this blob at the center. So this is basically a low-pass filter. And we did this for all these 40,000 kernels that we have. And we saw that in the Fourier space, actually a lot of these kernels look very similar. So we just came in clustered them. So what I'm showing you here is that for 3 different CNNs trained for parameterization in 3 different turbulent flows, I'm showing you for 2 of the layers, the cluster centers of the spectra of the kernels. And we see that there are a lot of similarities between what these CNNs have learned. They have learned a lot of low-pass filters, high-pass filters, and these interesting bandpass filters, and these turn out to be Gabor filters. So if basically you take a sine function, multiply with the Gaussian, you get this kind of wavelet-like patterns, and this is its Fourier transform, which basically pick up these wave numbers. So basically, a million learnable parameter in these CNNs turn into a few classes of spectral filters. Now, I should say that in the machine learning community, it has been known for over a decade that particularly for classification problems, CNNs can learn Gabor filters and more broadly wavelets. And even beyond the machine learning literature, in the neuroscience and sparse coding literature, it has been known that if you try to learn multi-scale localized oriented patterns, the kind of data that we have in climate science and in turbulence, actually these are the best or very useful basis functions to use. But what we found here is that even for when you deal with turbulence and climate data, actually we get the same kind of filters. Now, this can be useful because we can imagine that we can use this to develop some skeleton models for these CNNs that at least for the purpose of analyzing them and understanding what they are doing, we can exploit the fact that there's a lot of redundancy in what these kernels are learning, and we can try to develop end-to-end representation for these neural networks in the Fourier space. Now, we're not there yet. We have nonlinearities and there are layers, but there's a lot of work that's done currently in the machine learning community that we can leverage to make progress here. Now, fortunately for transfer learning and a number of other applications where we just update some layers of a neural networks, we can already use this and we can use this to make sense of what's learned. And in fact, the first paper that we published about this was actually was led by an undergraduate student at Rice. The paper was all about transfer and learning. But since then, we have used it for a number of other applications as well. I'm not going to go through the details, but of course, if you're interested, take a look at the paper and I'll be happy to chat. But basically, we have put all these ideas together and we have developed a framework to optimize and explain transfer learning in these kind of climate applications, where this idea starts from looking at the data from different systems in the Fourier space, something that climate scientists, physicists, applied mathematicians have always been doing. Then we can use some ideas from machine learning, like looking at the loss landscape to tell us what layers would be the best to retrain. And then by looking at the changes in the Fourier spectra of the kernels and the activations, we can connect these back to the physics as we showed in that paper. And now we have been using these to look at a number of other ideas, like to make the transfer learning or these kind of approaches more data efficient, explain things like pruning, and a number of other applications. I should also say that transfer learning is not just useful for subgrid scale modeling or just to go from one parameter to the other parameter. It's also an extremely useful method when you want to combine training sets that have very different amount of data. For example, it can be a very useful method to combine data from observations, like in our case from the balloons, with a lot more data that we have from simulations. And this is actually the application of transfer learning that's already made it very popular in climate science and in geosciences. And this framework that I presented can actually be used for those kind of applications as well. So with that, I'm going to stop. And what I want to emphasize is that by combining ideas from machine learning, from physics, and from applied math and numerical analysis, we can start addressing some of these major challenges that we have for applying machine learning to climate science. And so for students and researchers who are working on some of these ideas and some of these areas, there are a lot of opportunities to collaborate with climate scientists and make significant contributions to basically improving our capabilities to deal with extreme events and climate change. So with that, I stop here and I'm looking forward to your questions.
Yeah, thank you, Pedram, for really inspiring talk and pushing the boundary of this physics, explainable physics-informed machine learning. So if there are any questions, please put in the chat. I can also ask my questions first.
Go ahead.
Yeah, so I'm very interested in this result. You show the CNN can learn quite well the relationship between this pi parameter as well as a function of vorticities and string functions. And then it works better than the 1963 model. And I was wondering if you think there are values to look at the CNN learned result and then figure out what equations would faithfully describe the CNN.
Yeah, yeah. I mean, that's a great question, and I mean that's something we have been thinking about. I mean, one approach is to try to develop some again a skeleton model for these CNNs, right, and see to what degree we can simplify the combination of the wavelets that are learned. I mean, there has been a lot of work in trying to use wavelets for turbulent flows, right? And here, what's different is that we are using layers of wavelets with nonlinearities between them. So the question is, can we take this CNN that had 40,000 kernels and really reduce it to what is essential to have still the similar kind of performance, and then understand what it is doing, right, and connect that to the physics. So that's something we are pursuing. But also there has been some nice work by, for example, Mike Cranmer and others that you like, for some architectures at least, you can go and try to discover equations that represent what's learned in the latent space. So that's also, I think, another exciting direction that can be pursued. Yeah.
Cool. There are some questions in the chat. Pedram says, well, it's very helpful overview. Are you able to read the chat, Pedram? I can also.
Okay, I think I have to figure out how to. Oh, okay. Yeah.
Okay. AD asked, the low pass filter of weight matrices looks like the neural network is calculating some kinds of lower order derivatives of the flow. Can we use neural network results to better understand the system analytically?
Yeah, that's a great point. And that's something we have been looking at, but again, there are too many things to look at, so we haven't done a lot. But yeah, one thing to look at is whether these, you know, the filters and the wavelets are used to calculate some sort of derivative. And then the question is how they are combined to take care of nonlinearity. So certainly that's an interesting direction. Again, like developing some machinery so that this can be done rigorously. I think that machinery has to be developed, but certainly that's an interesting idea. I mean, there have been a number of papers showing that at least the first layer in some problems, they're really just taking some derivatives. But then what happens at the deeper and deeper networks? I think like that's a question to answer.
I want to break in and say people can also raise their hand on participants and ask questions orally.
So someone raised.
Ashutosh platform.
Ashutosh, would you like to ask your question?
Yeah, I think I should be able to let you. Are we able to log in to speak? Can't tell. Maybe you should type it in. I'm trying to turn on his mic.
Actually, I'm the host. I don't know if I'm the one who.
Okay. Yeah, you might be able to.
Oh, yeah, I think maybe I'm the one. Okay. Sorry.
Yeah, okay. There you go.
Oh, good. It works.
Okay. Can you hear
me
now?
Yes.
Yes.
Wonderful. Thank you for enabling that. Something was stuck. I'm not sure what. Okay. That was a wonderful talk. Actually, I'm kind of getting really interested myself. So a quick question for now. When we talk about this transfer learning, and you showed an example, I think, on an earlier slide too, where some learned model was tried, and then you found not enough data. I'm forgetting the context. It was backscatter context. And then you found, you know, you had to train something additional. And then you showed that now the better improved learned model was actually able to reproduce something fundamentally computed. Is it true that every time anything is ever learned or transfer learned or whatever, you would always have to check it against some hardcore first principles calculation to show that it's correct? So you could never really just use a learned model as is. You would have to validate it versus fundamental physics and then you're more confident you can apply it. And if you were to extrapolate again, you would say, oh, the extrapolation may not work. I would have to again do a fundamental calculation in some limited domain to check that the extrapolation is fixed up and then use it. In other words, I think you made that point several times that the reductionist approach is always, understandable, generalizable, and you sort of know what is going on. Whereas the machine learned thing is fast and efficient for multidimensional things, but you never know if you can really generalize it or not until you prove it. Is that a correct assessment of, some of your message here?
Yeah, I mean, that's a great point. And I mean, with the neural network application, of course, we can go and empirically test to see what the neural network is representing, to what degree it's consistent with the right physics. And us, and I think many other people are currently doing that more and more. I mean, well beyond just showing that you get the right PDF for the spectrum, we have been looking at what is, for example, CNN representing in terms of interscale energy and entropy transfer. And actually, they do a very good job. But sure, we don't have the machinery to do the same kind of analysis that we can do for a physical model with these kind of models. And that was exactly my point, that maybe developing these kind of skeleton models for neural nets actually would allow us to do reductionist science now on the neural networks. Because again, reductionist science, it's in the name, you have to be able to reduce something, yes, right? And then look at it rather than the whole idea of having an over-parameterized neural network. And that's why I'm excited about this Fourier analysis and stuff. But sure, I mean, eventually, and for a lot of these to be practical and reliable in climate science, especially when it comes to climate change projection, we have to be able to understand what these parameterizations are doing, when they break down, what kind of uncertainty they produce. So these are all active areas on research. But yeah, so I think that's where I think there's a lot of exciting stuff to do, including for students, postdocs, researchers who are coming from other fields and have other expertise to bring in.
Thank you.
Thanks.
And also just advertise, Pedram is moving to University of Chicago, probably looking for new postdoc students. So lots of opportunities. And John Wetterlaufer has a question. I don't know if John can unmute. John, can you unmute yourself to ask? Or maybe Pedram can help.
Okay, if you raise your hand, then I can see you in the list. Otherwise, I can't find you. Oh, okay. Yeah, okay. Go ahead.
Good. Works, yeah. Please go ahead.
No, I said it in the chat. I mean, we use path integrals to find optimal space-time paths. And for something like stochastic resonance, we can determine the precursor state for a rare event. So you mentioned some of these outstanding issues in your conclusion, and the question really is, have you considered using path integral methods?
So something we have thought about is to use the fact that these, like for example, the data-driven models now for short term can be very accurate, and so they are differentiable, or they can produce large ensembles, and to combine those with some of these other methods in like rare event sampling methods to better learn rare events. But I think that's like an exciting area to bring in the kind of tools that you are talking about and other tools that are out there, and combine them with these machine learning methods so that we can actually represent the tails. Because it's a major data imbalance problem, right? That when you try to learn from data, the tails are not frequent, so the neural network is not going to see them, right? So for whatever application that somebody is looking at, that can be a major issue. But yeah, I mean, I don't know exactly like the work that you are referring to, but certainly can be something interesting to look at.
Thanks.
Yeah, thanks. I'll send you an email.
Yeah, great.
There's another hand raised. Ashutosh, do you want to ask something again?
A follow-up question. I don't want to, hold up anybody else. So if there's nobody else with a raised hand, I'll ask my follow-up question.
Okay, there's actually one more question by Sina.
That's a great question, Sina, about what the spectral analysis works in non-periodic problems. So we have now also applied this to the Rayleigh-Bernard convection problem when you are periodic in one direction and then bounded by walls. And actually, in the numerical solver, we had Chebyshev polynomials. So still it makes sense. Again, it also depends on how you do your convolution. You can just close your eyes and apply convolution in the same way that you apply convolution in the like a periodic domain. But even if Yifei Guan, who is a postdoc in my group, he has done a lot of work and tried to actually adapt this for Chebyshev polynomials. So short answer is yes, you have to do some work, but you can still make sense of the spectral analysis of the kernels. But that's a great point.
Awesome. So Ash, Tosh, and then maybe we end afterwards. Yeah.
Okay, so maybe I'll ask my follow-up question quick. So would you see a value in taking some parts of the calculations you have to do with the reductionist approach, which, as you showed, are very, very, very slow, and so you're using these machine learning methods to capture the small scale stuff? Do you see any value in trying to improve the computational ability of certain parts of the equations by some large factor? Like if some method could be developed to improve fundamental calculation speed by a factor of 10 or 50, is there still any benefit from that, given that the machine learning approach is starting to do well?
So one thing I wasn't sure about is like in terms of making the solutions faster with machine learning methods or with other approaches?
With the first principles calculations, being able to be done, say, 50 times faster, is there any reason to now develop such speed improvements, given that we are starting to replace some of that with machine learning?
Yeah, I think it really depends on the problem. And I mean, sometimes even a factor of 10 improvement in the speed is not enough, right? And again, in climate science, like reducing the uncertainties is really the biggest problem. And epistemic uncertainty is one, but just doing longer simulations, many simulations from different initial conditions, even with perturbed parameters, right? These are all very important. So I think we are always looking for ways to accelerate the models that we have. So even if by having better hardware, by having better algorithms, we can accelerate the traditional tools, it's still like using methods that would enable us to make things even faster, or doing more simulations, or doing more ensembles. I think there is always value there.
Okay.
Yeah.
What kind of factor would you advertise as a useful target? 50, 100?
Okay, yeah, that's a difficult question. I think it really depends on the application.
Okay.
But yeah, it depends on who you talk to. I mean, there are people who want to take the output of a climate model, couple it with a model for natural hazards, couple it with a model for the financial stuff. And there, people want to have like models that are faster and faster. So it really depends on the application.
Okay, thank you.
Thank you.
So in the interest of time, Pedram, do you have time to answer another question in the chat?
Sure. Yeah, you think.
Yeah.
Still the same order. Yeah, so that's something we haven't looked at. I mean, it's still, because again, like there are the wavelets, but then there are different layers and there's no linearity between them. So to exactly understand what they do from the input to the output, it needs some work. And like a postdoc in my group, Hamid, has been looking at pruning and some of the other ideas that are out there, so that we can like understand what these are doing. So thank you.
Excellent. Well, you got lots of questions, and we're also a bit over time. So that's just thank Pedram again. Very inspiring talk. And I guess we'll see you again for the next GPC seminar on November 15 by Jeff Fellis, talking about planetary climate and paleoclimates. All right. So with that, thank you, Pedram, and I'll see you again soon.
Pedram, thanks everyone for being here.
Thanks, Albin.
Yeah. Thank you. Bye-bye.
Thanks. Bye.